Hello and welcome. Today's topic is axial tension and compression. Displacements in statically determinate systems. I have prepared 3 examples for today. The first one, calculate the diameter of the rod D and the elongation delta L. We have the dimensions of this rod beam or rod frame system and all the forces. We have the moment, the tensile strength, the compressive strength, and we need to calculate the diameter of the rod based on the strength conditions. And once we calculate the diameter, we can then calculate the elongation of that rod. So we have here a fixed hinge support with 2 reactions, vertical and horizontal. And we have a reaction in the rod. What interests us in this problem is actually only that reaction in the rod, so we can set up the sum of moments about point A relative to this fixed support here. And then one unknown in this equation will be that reaction in the rod. So to do this, to sum the moments at this point, we need the arm of action of each force. Well, let's look at these forces in this system. Force P, you can see the arm of action of the force relative to the moment pole, which is the shortest, that is the perpendicular distance from the direction of action of this force. Here's the direction of the force to the moment pole. So if we extended the direction of this force P, here is the shortest, which is the perpendicular distance, which is the arm of action. So it is A, as you can see. And now, continuous loading can be reduced to a resultant at the center of gravity. The center of gravity of a rectangle is simply at half the length. So the arm of action of this continuous load, well, will be like half of this 2A, which is A, and then here 2A to that point. So we also have that the moment is a moment. It does not act on any arm. We just take its value into the moment sum. And now this reaction, or rather the force in the rod, it is along the axis of the rod. And here this distance is not so obvious anymore. It's good to transfer it here to the right, here to make 2 triangles, which look like this. And based on that, to calculate that distance from the sines and cosines of those right triangles. So, the sum of moments about point A equals 0. And the equation will look like this. As I told you, we assume that clockwise moments about point A are positive, clockwise positive. The force P would turn us counterclockwise, and it is at arm A, so minus P times A. Adding, and now we reduce the continuous load to a resultant at the center of gravity. And this is the value of that continuous load times the length of the segment over which that continuous load lies. So Q times 2A, and this is the 2QA, which turns positively relative to the moment pole A. On the arm 3A, which is half of these 2A on which it lies, that is the center of mass and also 2A, together it makes 3A. And now minus S and times that arm. Now where did I get that arm from? Well, precisely from those triangles. If we were to write that there is y, that is this length, then y to 2a is the sine of that angle, which is sine 60. So y is 2a times sine 60. If we accepted this length as y, then y to 2a is the cosine of that angle, which is cosine 60. Or sin 30, whichever. It is the same value. So y is 2a times cos 60. And the entire length is e plus y, which is written here in parentheses. Okay, we want to calculate our unknown. That is the reaction in the rod, that is S. So we move S from the parentheses to the other side. We divide by that parenthesis. We can of course swap them around. And we insert numerical values. So P was given, A was 1 meter. And all the data here was provided in the task statement. So, by substituting these sines and cosines, we have that S equals 9.88 kN. Because I substituted force P, M, and Q as they were in the task statement, that is in kN. Therefore, the result is in kN. If I had converted to N, that is the basic unit, the result would be in N. but I didn't do that, so I have it in Kn. And what, with the force in the rod already known, we can dimension it. That is, we dimension the diameter based on the strength condition, that is, on stress. Stress for the strength condition we take as an absolute value, because once we know whether the rod will be stretched or compressed, we compare stress to the appropriate strength. The force in the rod has turned out positive, so the rod will be stretched. We always assume the force as if cutting. We cut this system, and here at the cut is this force, S. If it is positive, then the rod is being stretched. If it is negative, then the rod is being compressed. So our rod in this system is being stretched because the force turned out positive. Now that we know it is being stretched, we take the tensile strength. But if it were compressed, we wouldn't take it here. It would give us a negative force value. But we don't take it with a minus. We only take the absolute value. That's why I wrote it that way. Well, we have plus, and that's just how it looks. So the force is positive. The rod is being stretched. So we take the tensile strength. Therefore, we have the force and the cross-sectional area. The cross-section is circular. The area of the circular cross-section is recorded as, because the area of a circle is pi r2, but if we write diameter instead of radius, it is pi d2 divided by 4. This is often used in strength calculations. The area of the circular cross-section expressed with diameter, which is pi I d224. The force in the rod is 9.88 times 10 to the 3n, already in base unit. Tensile strength from the problem statement is 80 megapascals, so we can already write from this formula. That is, force divided by area of the cross-section less than or equal to 80 megapascals. That is times 10 to the 6. Now we rearrange it. Here, we multiply pi dd24 by the reciprocal, which means 4 goes up. We divide by 80 times 10 to the 6. We multiply by d2. These are standard mathematical transformations. We take the square root of this, and it turns out that the diameter must be greater than or equal to 125,000 meters. Because everything was in base units, if we move the decimal 2 times to the right, or multiply by 100, then we have in centimeters. So the diameter must be greater than or equal to 1.25 centimeters. Having already dimensioned the diameter, we can calculate the elongation of the rod. The elongation of the rod formula is the force in the rod, times the length of the rod divided by Young's modulus, times the area of the cross-section. The area is pi d24, I remind you. Our d must be greater than or equal to 1.25. We can round slightly upwards, which is 1.3 centimeters. So I substituted here. This is in centimeters. I want the result in base units, so converting back to meters. I can write it as times 10 to the minus 2. And this diameter must be squared, so this is how it is written. The result comes out in square meters, because I converted to base units. Young's modulus from the problem statement was 2 times 10 to the 5th megapascals. So 2 times 10 to the 5th times 10 to the 6th, that is 2 times 10 to the 11th. And the calculated force in the rod is 9.88 times 10 to the 3rd, already written in base unit, in newtons. And everything in base units is substituted into the formula. And it comes out. On the calculator, we get a result in the base unit, which is in meters. That is the extension. That is 3.8 times 10 to the minus 4th. If I multiply by 10 to the 3rd, it will be the result in millimeters, which would be 3.8 times 10 to the minus 1st millimeter. And if I move the decimal point left again, so that there is no 10 to the minus 1st, it will simply be 0.38 millimeters. We measured the rod and calculated its extension. So that's everything that was asked of us in this task. If you have any questions about the solved tasks, I encourage you to ask questions under the video. I'll try to answer. I also recommend our other productions. And that's all. Goodbye. Greetings. Bye.